In this video, we move on to Chapter 4. We're going to cover the concepts of Chapter 4. This is a discussion of reactions in aqueous solution. In particular, we're going to look at three important classes of chemical reactions. One of the important emphasis points here is that the reactions that we're looking at in this chapter are primarily carried out in water. And we'll see why that's important in a moment, if you don't already know. We'll look at how we write out reactions in water, particularly for ionic compounds. And we're going to be looking at aqueous ionic reactions. And the three reactions that we'll look at are precipitation reactions, acid-base reactions, and redox reactions. These three reactions are very important. They're occurring all over the place in the environment. They occur in biological systems. They are the means by which we derive energy from food. They are used very regularly in industrial environments. They're important and used in government and compliance laboratories. So these are very important reactions. They're used all over the place, and you're carrying some of these reactions out inside of you right now. So it's important that we understand how these reactions occur, and we have some nice rules that very quickly allow us to understand how these reactions are carried out, and we can make predictions of literally thousands of reactions based on some simple rules that we'll learn in this chapter. As we start off, let's look at one of the properties of water, which turns out to be really important in aqueous chemical reactions. And for this, we're going to compare two molecules, a molecule of H2 in the upper left-hand corner and a molecule of H2O on the upper right-hand corner. A molecule of H2, of course, has two hydrogen atoms, and the electron distribution around the two nuclei is evenly spread. We'll look at this in a lot more detail when we get to the later chapters, but sufficient to say here, we'll just get a basic picture. The electrons are spread evenly around the hydrogen molecule. So we would say that that molecule was nonpolar. There's a kind of a even symmetry to the electron distribution. For water, in contrast, water turns out to be a bent molecule. It exists at an angle of approximately 104.5 degrees, where the oxygen is in the center and the two hydrogens come off of the oxygen atom. And the molecule is being slightly bent, ends up being what we call polar. That is, if you look in the upper right-hand corner, the oxygen molecule is drawn in red, and the oxygen atom is drawn in red, and the hydrogen atoms are drawn in blue. And the oxygen atom is partially favored for electron localization. So there's more electrons around the oxygen, and there's fewer electrons around the hydrogens. And because of that, the molecule is what we call polar. It has a negative pole and a positive pole. Now this is water being a polar molecule in and of itself is not highly important. Well, it's important, but it turns out that there's a lot of polar molecules. But on the next slide, I show a lot more data. Now, this slide is taken from our course in environmental chemistry. So this is a slide from a graduate course. So you won't need to know this, but I'm throwing this up here just for you to look at to kind of give you an understanding of how important water is. And you can look at this slide, or there was a NOVA show on PBS recently that looked at the properties of water. And it was, I didn't see much of it, but it seemed like it was a nice show describing some of these basic ideas, but a lot more artistically and taking a lot longer to do it. The key points here at the top: water is ubiquitous on Earth. Water is everywhere. It's inside of us, and it's in the atmosphere and the oceans. The surface of the Earth is covered with water, and it turns out that a lot of the minerals in the Earth have a lot of water as well. There may be more water in the lower geological levels of the Earth than there are on the surface of the Earth. Water is really important in chemistry, both as a solvent, and a solvent is the reaction medium in which another reaction occurs, but also as a reactant itself. Now, why does water have all these interesting properties? Well, the first three things listed on here are things that we'll cover in Chapter 6. So we don't really need to understand these fully now, but it turns out water has the highest heat capacity of any liquid per gram, except ammonia, liquid ammonia. It has the highest enthalpy of fusion of any common liquid and the highest enthalpy of vaporization. Now, what do those first three things mean? Well, it really boils down to this one simple idea. Water can absorb a lot of heat, and it can release a lot of heat. Water is a great storehouse for energy, much better than most any other molecule. Water also has the highest dielectric constant of any common liquid. And the dielectric constant for, the electrical engineers will understand that in our class, but most of us aren't electrical engineers. What is a dielectric constant? It's the ability of a material to separate two charges. The next thing, water has the highest surface tension of any common liquid solvent. So what does that mean? It beads up quite well, which is why, of course, bugs can walk on water. Water is more dense as a liquid than a solid, and this is really key for environmental reasons and for life on Earth. Most liquids, when they freeze, their solid is more dense and they sink to the bottom. Well, water is a little bit different. It has its maximum density at a few degrees Celsius, right above the melting point. And so ice floats on the top. And of course, when lakes and streams or rivers freeze during the winter, the top layer freezes first, and that insulates the underlying layers where organisms can continue to live during the winter. Turns out it's transparent in the visible and UV region, which allows photosynthesis to occur in water, and it's an excellent solvent. So these are all really important properties. This is just an overview for those who are in biology or nutrition and dietetics. These are things that you might be interested in, but you won't need to know all the information on this slide. This is just more for your edification. But moving on, let's look for our reactions in this chapter: the precipitation, acid base, and redox. How does this work? Well, we'll start off looking at an ionic compound dissolving in water. Ionic compounds are usually very hard, stable, robust structures. But if you throw them in water, they fall apart. Like when you take water crystals, of course, salt crystals. If you take salt and try and melt it on your stove, you'll run into trouble. Salt doesn't melt on your stove. It's a very robust structure. But if you throw it into water, it just breaks apart. How does that happen? Well, the water molecules surround the negative ions with their positive poles. So those hydrogen ends go towards the negative ions and they carry them away. The water molecules point their negative ends, that oxygen end, towards the positive side. So if we had sodium chloride for example, that positive would be a sodium ion. The oxygens would be surrounding it, and that's a very stable structure. And so that pulls the salt away. And the fact that it has such a high dielectric constant is why water dissolves salts so much better than other polar compounds. Now let's go back and let's look at this just in a little more detail. And this is given to to give you a mental image of what is involved in breaking up an ionic compound. We'll see when we get to later chapters. When we get to chapter 9 in particular, we'll look at bonding an ionic compound. But before we get there, it's important to say they're stable. So we can break up ionic compounds two ways. The first way is how you do it in lab. If you wanted to just break it up and form separate ions. You can melt the salt, but this has to be done at high temperature, often over 1,000 degrees. Then you have to heat it up further to its boiling point. So that's very high temperature, sometimes over 2,000 Celsius. When the ionic compounds vaporize, they don't vaporize as ions. So if I take sodium chloride and I melt it and boil it, sodium chloride that comes off as sodium chloride molecules. That is an NaCl molecule. And then if I want to break that apart, I'm going to have to hit it with deep ultraviolet radiation to dissociate, and then, of course, appropriately ionize into the M plus and X minus. So if I want to break up an ionic compound into its ions, I have to hit it with a high, very, very high temperature, roast it in a furnace, take the vapor, blast it with UV radiation. Or I can drop the ionic compound into water at room temperature. Hopefully this illustrates to you the importance and the power of water for serving as a solvent and how it interacts with ionic materials. Now, once we've formed an ionic solution, of course, the ions really are broken up in the water. So if I have sodium chloride as an example, I will have Na plus ions and Cl minus ions in water. And this picture, in this figure, serves to illustrate this. Up at the top are 3 light bulbs. And these light bulbs are all connected in a circuit. Each one is in a circuit, and in that circuit you have a beaker. So you've got 2 electrodes in the beaker. And the one on the far left is just pure water. So if I put pure water in there, pure water turns out to be an electrical insulator. It won't carry current. That's because the water molecules are not broken up into ions, so there's no free charges floating around. In the middle, we have solid sodium chloride. So I have a solid salt that, you can see the crystal lattice there, but those ions can't move. They're frozen in place. You see the rows of ions. They're trapped like soldiers marching in line. They can't get out of their place. And so if I apply voltage, they still don't move, so I see no light because no current gets carried. But if I throw the salt into the water, then I have the figure on the far right. Now the sodium ions and the chloride ions can move through the water and carry the electric current, and the light bulb comes on. That helps to prove to us that the ions are indeed free in solution and can move. Now, when we have ions in solution, we want to be able to indicate how many ions are in solution. We have what we call a concentration. Now, in chapter 3, we had moles and we had grams. Once I throw material into water and it breaks up into ions, I need to account for where those ions have gone and how they're going to behave. And so we have something called molarity, which identifies the concentration of the solution. If I have water and I have no salt in it, the molarity is 0. If I put a small amount of salt in the water, I have a dilute solution, and the molarity is low. If I throw a lot of salt in the water, the concentration is high, and the molarity is high. And molarity is shown at the very bottom of this slide. Molarity is defined as the following, and this is a definition you need to know because you will use this semester multiple times, and you'll use it a lot when you get into Gen Chem 2. Molarity is equal to the moles of solute divided by liters of solution. So the solution is the solvent plus the solute. So the solute is the thing that gets dissolved in the solvent to make the solution. So let's take another example. Let's continue to think about sodium chloride. If I take sodium chloride and if its formula mass is approximately 58 grams per mole to a couple of significant figures, if I take 58 grams of sodium chloride and throw it into water to make a liter of solution, I will have put 1 mole of that ionic compound in solution. Therefore, its molarity will be 1 molar. We'll work with this later, and we'll do examples when we get to the mechanics chapter or section or video on this chapter. One of the most important things that you're going to need coming into this chapter, you learned in chapter 3, and that is the common ions and their associated charges. So let's take an example. Barium acetate, that's a compound we might have looked at last chapter. Barium is a group 2 ion. Acetate is a polyatomic ion. Barium has a 2+ charge on it. Acetate has a 1 minus, so barium acetate has a molecular formula BaC2H3O2 taken twice. And if I throw that in water, then it turns out this is a soluble salt. The barium and the acetate separate from one another, and I will have barium ions and acetate ions, and I will have twice as many moles of acetate ions as I have barium ions. Likewise, we can have our next compound, that's ammonium phosphate. You recognize the charge on ammonium as +1 and on phosphate as 3-. That's why we need to have NH4 taken 3 times with PO4. We put that in water and we will get 3 NH4 pluses and 1 PO4 3-. This serves to illustrate that we'll need to know those ions and their charges and how they work when they hit solution. Here is a summary then that pulls together some basic ideas that we have from molarity. The green, the yellow, and the beige box would have come from chapter 3 that relates mass of a substance in solution to the amount of substance in a solution. And then with Avogadro's number, that would give us entities of substance in solution. So the difference here is these are all in solution, not simply based on their mass themselves, because there's now a solvent. So now we add a fourth box, and that is the volume of solution. So the volume is related to the amount by the molarity, that big M, moles per liter. We'll do some practice problems in the mechanics section later. Now, we're going to spend the rest of the time looking at the rest of the time on precipitation reactions, looking at chemical reactions. So here we have a common chemical process. This is precipitation. In the upper left-hand corner, we have 2 beakers, 2 Erlenmeyer flasks that have solutions. The one that's clear is silver 1 nitrate, or most commonly called silver nitrate, because silver usually just has one oxidation state or charge state. Then the yellow solution is a sodium chromate solution, Na2CrO4. If we mix these 2 solutions together, the one on the right is the resultant. You see the big pile of red sitting at the bottom. These 2 have reacted by the silver ions and the chromate ions coming together and crashing out of solution. Now, notice this. The silver interacts with the chromate ion to form an ionic compound that is silver chromate, which is the red material. So then the question is, what happens to the nitrate ions and the sodium ions that were present in the precursor solutions? Well, they really don't do anything. They're still in the solution. So if you look on the right-hand side, you've got the red solid at the bottom. Up above is a liquid, and that liquid has sodium and nitrate ions floating around. They're what we call spectator ions. They don't participate in the reaction. They have to be there because to get silver in solution, we need nitrate. And to get chromate in solution, we need sodium, but they don't participate. And if I take the beaker or the Erlenmeyer flask on the right side and I filter off the red material, the sodium and the nitrate are carried away. There are 3 ways that we can specify this chemical reaction. We can write out what we call a molecular equation. We can write a total ionic equation, and we can write a net ionic equation. Each one is important in a different situation. The molecular equation, for that, what we do is we write down the starting materials as molecular systems. We write them down as their compound form. So silver nitrate would be AgNO3, and we write next to that AQ to indicate it's dissolved. And then the sodium chromate is likewise written as Na2CrO4 with the aqueous next to that. And our product then is written in molecular form. We see it written down as Ag2CrO4, but here we write an S next to it to indicate we're forming a solid. That's the driver for this reaction. And next, we write +2 NaNO3, so we write our spectator ions combined together, but we know they're not. They're simply an aqueous solution as a dissolved salt. Turns out there's ways to extract the sodium nitrate from this, but we will not get into them. That's beyond the concerns of this class. Next, we can write this as a total ionic equation. Now, the total ionic equation takes all of the soluble salts and breaks them up. So, for example, silver nitrate is written as 2Ag plus 2NO3 minus. And sodium chromate is written as 2Na plus CrO4 2 minus. And on the product side, we still write Ag2CrO4 as one unit because that's now an ionic solid. So that's written as a solid. But then the soluble salts on the product side are written as 2Na plus and 2NO3 minus. And we write phases of AQ next to all the soluble ions. Now, if you look at the total ionic equation, you'll notice that you have, for example, 2Na plus on the left, 2Na plus on the right. We have 2NO3 minus on the left and 2NO3 minus on the right. They're spectators. They don't participate in the reaction. So we can get rid of those, and we can write what we call the net ionic equation. This is only the ions that really changed during our process. So we would write this out, 2Ag plus aqueous plus CrO4 2 minus aqueous goes to Ag2CrO4 solid. That's the net process that occurs when we mix these together. The total ionic equation shows all the soluble ionic substances dissociated into ions, so the spectator ions are still present. Even though they're not participating, they're written down in the reaction. The net ionic equation eliminates those spectator ions. And so we only have the ions that are reacting. And as far as this goes, most times, if you look in, for example, tables, government published tables or industrial tables or research publications or in most more advanced texts, you will only write down the net ionic equation. There's no reason to write the others. It's just to save time. It's more efficient. So here's our aqueous reaction with the three types of equations. And we've already seen this. We know our molecular equation now. We know our total ionic equation and our net ionic equation. And for what it's worth, we usually write the net ionic equation. Sometimes we write the molecular equation to indicate how we got the materials present. The total ionic equation is written fairly rarely. It's somewhat more tedious and not as efficient. So our first class of reactions, the one that we've just looked at, is the precipitation reaction. A precipitation reaction takes two soluble ionic compounds, that is, ones that dissolve in water. You mix them together and they react to generate an insoluble product. That is, a solid falls out of solution or crashes out of solution or precipitates out of solution. It produces a precipitate. The precipitate forms through the net removal of ions from solution to produce the ionic compound. And while it is possible for more than one precipitate to form in such a reaction, we'll just worry about ones where only one precipitate forms, and that's the vast majority of cases. So let's look at a typical precipitation reaction, and that is the reaction to produce calcium fluoride. So we can take sodium fluoride, which is a soluble salt, as we'll see in a moment, with calcium chloride, which is a soluble salt, to produce calcium fluoride, which is a insoluble solid material, and then sodium chloride. And then sodium ions and the chloride ions turn out to be the spectators, so our second equation is the total ionic equation, and the third equation is the net ionic equation. This is the process that occurs. So how do we know that calcium fluoride is going to precipitate? Well, we know by doing the experiment, but we also have a set of rules that allows us to predict a very large number of ionic reactions and whether they'll occur or not. So for example, if I took sodium fluoride and reacted it with potassium chloride, nothing would happen. There would be no net ionic equation because all the ions are soluble. So if we want to predict whether a precipitate forms, we look at the ions that are present, and it says here, consider all the possible cation-anion combinations. That's what Silverberg says. It's actually simpler than that. You only have to look at 2, and we'll look at those when we go to the mechanics section. And then we use the solubility rules to decide whether any of those combinations is insoluble. If it's insoluble, a reaction occurs. If they're all soluble, then there's no reaction. And here are our solubility rules. You should have these, you should print this slide out and have these available to you. We're going to use these quite regularly. Hopefully you'll get comfortable with them and know quite a few of them as we finish up this chapter, but you'll always have this slide, this table available to you. So this tells us what ionic compounds are soluble and what are insoluble. It's really quite nice. Actually, we used to memorize these rules because with 7 simple rules, you could predict literally thousands and thousands of reactions rather than having to memorize all the reactions. So here are the rules, and let's walk through these. On the upper part of this table are the soluble compounds. These are the ones that dissolve in water and don't readily precipitate. All compounds of group 1, lithium, sodium, potassium, rubidium, cesium, all the compounds, ionic compounds of those species, as well as the ammonium salts, are all soluble. And there are exceptions to this, but this is the large majority of compounds. All the nitrates, the acetates, and most of the perchlorate salts are soluble. All the chloride, bromide, and iodide salts are soluble except silver, lead 2, copper 1, and mercury 1. All fluorides are soluble except those of lead 2 and group 2. All sulfates are soluble except those of calcium, strontium, barium, silver, and lead 2. Now, when I said mercury 2 above, you'll notice it's Hg2, 2+. That's 2 Hg plus 1 atoms stuck together. Mercury's a little unusual that way. So it's a special ion, and that's why we call that mercury 1. So these are the soluble salts. Now, the remainder tend to be insoluble, but these are the ones that we need to focus on. The metal hydroxides in general are insoluble, except, of course, the group 1, which we knew from above, and the larger members of group 2, calcium, strontium, and barium. All the carbonates and phosphates are insoluble, except those of group 1 and ammonium, which we knew from the upper panel. And all the sulfides are insoluble, except those of group 1, group 2, and ammonium ion. Now, we'll see how to use this table, and we'll do quite a few examples when we get to the mechanics videos. So here's the precipitation of lead iodide. It says a metathesis reaction. It's a precipitation process. Sodium iodide reacts with lead nitrate to form lead iodide and sodium nitrate. We'll see how this works. Now, for each of these reactions, we can also calculate how much material will be reacted or produced. And so we can use this table here, this flow chart, which is very similar to what we saw in chapter 3. In the middle is the important part. That's the amount of substance that reacts. So, for example, in this upper slide, the last slide we looked at, the sodium iodide and the lead nitrate, we can see it's a 2-to-1 ratio. We need 2 iodides for each lead. And so that would be the balanced equation that would tie together amount of substance A with amount of substance B. And we can relate these to their masses, to their number of entities, or to their volumes by their molarity. So that's all on precipitation reactions. We'll do examples later. We're going to move on to acids and bases. We're going to look at acid-base reactions. These are really important, but we're going to start off really simply. What is an acid? Well, it turns out acids are generally sour materials. Lemon juice is acid. It tastes sour. Vinegar is sour. Acids are corrosive. They generally dissolve up metals and they corrode materials. The non-metal oxides are the species that are acids, and they tend to react with bases. Bases, on the other hand, base means it comes from the earth. Bases tend to be bitter. They're metal oxides. And they tend to react with acids. Now, there are multiple different acid-base systems. And here's three most important ones that you will encounter as an undergraduate. And the first one is the one that Silverberg uses for Chapter 4. For the Arrhenius acids and bases, an acid is a species that is an H plus donor, that can basically a molecule that can give up H plus to other species. And a base is something that is a hydroxide donor. So for example, HCl, hydrogen chloride, when it goes into water, it's hydrochloric acid. It's a H plus donor. A base might be like NaOH, sodium hydroxide. When that goes into water, it forms sodium Na plus and OH minus. The Bronsted-Lowry definition is a little bit broader. It encompasses all the Arrhenius acids, but it includes some others. And for the Bronsted-Lowry definition, an acid is a proton donor, and a base is a proton acceptor. A bigger definition yet comes from Lewis. And you'll see this a lot in organic chemistry. We won't spend any time on Lewis acids and bases in this course. But a Lewis acid, as you'll see later, is an electron pair acceptor, and a Lewis base is an electron pair donor. So we're going to focus on the Arrhenius definition. And in this case, an Arrhenius acid plus an Arrhenius base will always mix together to form salt and water. So here's the definition written in your text. An acid is a substance that produces H plus ions when dissolved in water. That could be a Lewis or a Arrhenius or a Bronsted-Lowry acid. So here we see HX. In this case, the H2O is written right above the arrow. The H2O doesn't participate in the reaction, but it is necessary for the reaction to occur. That's what allows HX to break up into H plus and X minus. A base is a substance that produces OH minus when dissolved in water. That is our Arrhenius definition. So MOH, when it hits water, then forms M plus and OH minus. An acid-base reaction is also called a neutralization reaction. It neutralizes, the acid gets neutralized by the base and vice versa. The neutral solution is the water that's produced. Now, when you have protons in water, they generally don't float around by themselves. We'll write that down that way. We'll write it as H plus, but sometimes people will write it as H3O plus because the protons are so reactive they tend to stick to the other water molecules. So this is kind of an important picture to keep in mind. Now, here's a list of some common acids and common bases. And we've broken them into different groups. We have what we call strong acids, and there's really only 6 or so common strong acids: hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, sulfuric acid, and perchloric acid. There are a couple of other common strong acids, but these are the biggies. Now, if something is not a strong acid, it's generally a weak acid. So if it's an acid but not a strong acid, it's weak. And there are literally thousands of weak acids. Your book has listed 3 important common ones. Hydrofluoric acid, which is a very dangerous substance. It's not dangerous for its acidity, it's dangerous for the fluoride that's in it. Phosphoric acid, which is a common weak acid. That's used in Coca-Cola and a lot of sodas. It's used in a lot of foods to give a tart flavor. Remember we said acids are sour? Of course, no one likes to eat just straight sugar. Fruit is much better, right? So fruit, of course, has acids in it. And so to simulate the food flavor, you need sweet plus sour. And phosphoric acid is a cheap way to give you that sour flavor. Acetic acid, which is the acid in vinegar, is also a weak acid. And there are many, many more. The strong bases are fairly few. They're the group 1 metal hydroxides. We've got sodium and potassium, but lithium, rubidium, and cesium are also strong bases. And then calcium, strontium, and barium hydroxide. Now, magnesium hydroxide is a group 2 metal hydroxide, but it is insoluble. When it does dissolve, it breaks up, but it is generally insoluble. So solubility plays an important role here. So sodium hydroxide is like red devil lye. Obviously, you wouldn't want to eat that. That's very nasty, dangerous, corrosive material. Milk of magnesia is magnesium hydroxide. It turns out that your body can tolerate plenty of sodium, but magnesium is a bit troublesome. It's a diuretic. It pulls water out of your system. That's why you can't drink seawater. It's the magnesium content that gets you, not the sodium content. So when you drink seawater, you end up excreting more water than you took in because of the magnesium content. And there are literally thousands of weak bases, but ammonia is shown here as one common example. So you should have the table of the strong acids and strong bases printed out, because we'll use this semester. You should know what the strong acids are and the strong bases are. To compare these electrolytes, we can look at this picture, and it's similar to what we saw earlier. On the left-hand side, you have a strong acid solution. On the right-hand side, you have a weak acid solution. So on the left-hand side, for example, you might have hydrochloric acid, and you can see that you have a lot of electric current carried, and so the light is very bright. On the left-hand side, you might have, for example, a vinegar solution. That's a weak electrolyte, and it is more resistive, and it doesn't carry current as well. When you get to General Chemistry 2, there'll be a lot more detailed look at acids and bases, and you'll see how to quantify these effects. So now let's go back and look at the strong acids. We'll only do calculations in this class on strong acids. So just those that were listed in the upper table about strong acids and the strong bases. So the strong electrolytes we'll look at for acid-base systems, and we can use our basic molarity calculations. So for example, we could take 25.3 milliliters of 1 molar nitric acid. How many protons are there? Well, we know nitric acid is a strong acid, so we take the molarity and the volume. If we take the product of those two, that will give us the number of moles. And if we take the number of moles and multiply by Avogadro's number, we will get our answer. Next up, there are important gas-forming reactions that are acid-base reactions. And you'll have seen these before. Maybe if you ever made a volcano, one of these volcanoes for your science class or for a science fair. Use baking soda and vinegar. The reaction here is sodium bicarbonate reacts with, in this case, acetic acid to form sodium acetate. But you also get carbon dioxide and water because the product is H2CO3, but H2CO3 is carbonic acid, falls apart in water, and releases CO2 into the air. Next, we'll look at acid-base titrations. We won't do calculations here, but we'll do this later. A titration is a reaction that is very controlled. You take controlled volumes of material, and based on these, you can deduce concentrations for unknown materials. So in titration, the concentration of one solution, which is the known solution, or our standard, is used to determine the concentration of another unknown solution. And acid-base titrations, the standard solution of base, and you can have standards of acid as well, is typically added to a sample of unknown acid or unknown base. So you can have standards that are alkaline or standards that are acid. To know when you've reached the end of the reaction, when you've got chemical equivalence, we use what we call an acid-base indicator. And usually this will show us a change in color when we've reached the equivalence point. So the equivalence point is when you've reached stoichiometric equivalence, the moles of acid equals the moles of base, and we've neutralized our system. Turns out that the end point is where we see the color change. There is a little difference between end point and equivalence point, but for this course, we'll treat them as the same. So here we see a titration. We take acid, we're titrating it with base. We add the base through the upper device that's called a burette. As it hits the acid solution, it starts to react. And eventually, when you've neutralized all of the acid with base, you get a change in color. You get a pink color in solution. You can read the volume of how much material you've added, and therefore you know what your concentration is. Now that ends our first concepts of Chapter 4. We'll move on to more concepts in our next video.